Okay, so we're very pleased today to have Kiryung Lee give this week's 1W-MINDS seminar. Kiryung is part of the Department of Electrical Engineering and Computer Engineering at Ohio State University. His research develops mathematical tools, including optimization methods for various inverse problems and applications to signal processing and machine learning. He's also won the NSF Career Award, and today he'll talk to us about Max-Affine regression. So please go ahead.
Hello, everyone. First of all, I really appreciate Wei-Lin and other organizers for inviting me to One World Minds seminar series. It has been very successful. I'm very happy to participate in this seminar series. Today, I'm going to share our recent progress with my two graduate students, Seonho Kim and Haitham Kanj. Seonho is my fifth year PhD student who will defend later this month. I will join Geico next year. And Haitham is my third year graduate student. And this talk will cover two research done by each of them. Actually, they worked together on these two topics. We'll talk about the Max-Affine regression as a solution to the nonlinear relationship between variables. In particular, we'd like to focus on variations that address the presence of outliers and select active variables to explain the output variables. In real-world applications, we often observe very special structure in the relationship between data. In like average weekly wage data, so mean weekly salary will vary depending on years of experience and years of education. In particular, as you observe, how it is determined as a combination of like two variables. And it's not easy to model it as simple linear model. And likewise, if we will consider housing price as a function of the status of lower population and the average number of the rooms. And as we observed, the dependence of the price on these two factors is not simply explained as a linear model. It's highly nonlinear, but still it conveys some certain structure to further investigate. In particular, the convexity or concavity of the shape has been frequently used in economics and finance and other engineering applications. It has long history to utilize this structure in explaining the relationship. So we're interested in approximating this convexity or concavity as piecewise linear model that will simplify the relation with certain approximation error. But with this simplification, we are imposing the interpretability. That's very important to understand how the output variable is determined by the input variables. This is our fitting with respect to certain method to explain the data. As you see, the relation can be explained as the localized linear approximation. That is, if you restrict the range of variables into certain area, then we see some clear and easy to interpret linear relationship among the variables. But how we partition the area of the parameters, that's not very simple. That's what you want to identify. Once you identify how you partition the regime of the variables, then we can get a very simple and linear relationship. That's what you want to pursue in this talk. And mathematically, so we'd like to describe convex piecewise function as the maximum of k linear or affine functions. That's our key model in this talk. So we can relate output variable y as the maximum of the linear combination of input variable up to some intercept. We are taking the maximum of these affine models. So here is some toy illustration. In the univariate case, if you consider these three colored linear models, blue and black and green, and by taking their maximum, so it can be a convex piecewise linear function. I mean, the convexity is obvious consequence because the epigraph of the maximum is given as the epigraph of intersection of the epigraphs of each component model that should be shifted half spaces. That's the reason why this Max-Affine model is a convex function. Actually, this Max-Affine model is a very special instance. There has been line of mathematics that investigate more broader abstraction of this model called the tropical algebra. From the algebraic geometric point of view, they considered broader objects called like a tropical algebra that consists of tropical polynomials and rational functions. Actually, Max-Affine model is called as a tropical polynomial in their terminology, and there is more generalization with the different algebra. If we adopt particular max plus algebra, then it's written as a tropical algebra. Furthermore, the Max-Affine model can be utilized to understand very famous deep learning models. If you consider deep neural network with random activation function, then it can be written as the difference of two Max-Affine functions. In particular, as we consider the non-negative weights on fully connected deep neural network on the second and higher stages, then it reduced it to Max-Affine model. So in that sense, the convexity can be useful in simplifying the model, but it obviously adds restriction on its utility. So we are covering how we estimate parameters for Max-Affine model today, but our group is investigating how to extend it to the different Max-Affine case. The regression problem has been usually solved as a least squares problem. So we want to minimize the fidelity among our observed data, yi, where n is the number of observations. With the data generated through our Max-Affine model, we want to tune the parameters to minimize the square cost function as the least squares. And there has been several papers to address the optimization for these least square approaches, including the Magnani and Boyd and Hanna and Dunson and Gauss and the work by my own students. And one issue with the least squares fit is if there exist any outliers in the data set, then least squares is highly sensitive. In particular, for example, if we revisit the monthly salary data by injecting a few outliers, the majority of data are colored with blue, and there are a few outliers colored in red. And by injecting those outliers, and we can significantly bias our fitting. So as you see, the fit curve, the Max-Affine curve is quite separated from the majority of the data point. So this is something we'd like to address in the first part of this presentation. So one well-known approach in statistics is the least absolute deviation. In the least squares, we'd like to minimize the energy of the error by fitting our observation as the model, but in LAD, so we'd like to assume that the error shows a sparse pattern. So that means most of the errors are very small or negligible or zero, but there will be a few large errors. That's how we model the outliers as sparse noise. Then in that case, minimizing the L1 norm of the error is a natural choice. It has long history in statistics, including the textbook in 83. And that's the framework we'd like to utilize here. Like empirically, if you compare the LAD fitting to least squares fitting, then as you will see, I mean, this is what we implemented with our own algorithm that I present later. But with LAD fitting, so we'll see that the fitting curve is closer, much closer to the majority of data points. That's what you want to achieve. So one challenge is, I mean, for both the least squares and the LAD, and the cost function itself has no problem because it's simple convex function, but the problem arises with nonlinearity of the model. Although, I mean, it is given as some composition of several linear models. Still, it is nonlinear. It turns the entire optimization non-convex. So it is important to invent an algorithm that will provide the desired parameter estimate with reasonable amount of computation. So we will consider some variation of alternating minimization for this robust regression problem. And the idea is, given our current iterate of parameters, beta 1 to beta k, that correspond to the direction of the hyperplane representing its affine model. And we'd like to partition the entire space of the variables into k subsets. So that it's depending on which affine model achieves the maximum, then we can partition the entire space into k disjoint subsets. We also need to introduce the boundary where we see the tie in determining the maximum. But if we assume absolutely continuous probability measure on the input variables with respect to the Rubin measure, then the coincidence of observation on the particular boundary will be 0 all the time. So let's not worry about the boundary. So we are only interested in the CJs, that's the cells corresponding to the maximizing index with respect to the J's affine model. The algorithm consists of the iteration of the following update. So given the current parameters, the beta j_t, then we determine the set. Actually, we don't need to calculate the geometric object. We only need to, for each sample xi, we only need to determine the label, so which model achieved the maximum with xi. So that it's, we only need to evaluate this indicator function. Xi belongs to tj. And it is just a simple function evaluation, just compare like a k evaluations. It can be computed quickly. Once we updated these labels and we construct the cost function as the weighted summation of the absolute error of the fitting with respect to the J's model, there is no more maximum because we already know the which. Oh, there's a question. We will discuss the initialization later. So for now, so we assume that the initialization is given. I'm explaining how to update. Yeah, thanks for the question. And this updated rule is not, random recipe, but it is following the well established principle in optimization called Gauss-Newton method. The idea is if we make our model linear, the linear LAD has been well studied, and we can use gradient descent or any other method. Actually, linear LAD is cast as a linear program, and there are many well-known methods for linear program, including simplex method. But the difficulty arises with the nonlinearity of the model, and the idea behind Gauss-Newton method is globally, the model is nonlinear, but given fixed previous data rate, we can locally linearize our model through the derivative. But the model is actually not differentiable, it's non-smooth because of max function, where we can introduce the notion of the generalized derivative by the Clark. Then once we linearize the model locally, then we can substitute the Max-Affine model by using the gradient. Then we can solve the resulting the linearized LAD by just linear program. That ends up with this alternating minimization. And after partitioning, the remaining question is a simple linear program. So we can use simplex method if the size is small, but in general, for large scale, there has been several ADMM proposed with their convergence guarantee. So here is the illustration of its performance. Let's inject 20% outlier on the mean weekly wage data. And I'm just comparing the performance of the least square space approach. There's alternating minimization, that LSPA. SGD is the stochastic gradient for least squares developed by my own student, Seonho. And robust PA is the new algorithm also developed by Seonho for this particular presentation. And as we compare the performance here, for real data, we don't have access to the grounded truth. There's no grounded truth. The only way to assess the performance is only through the validation. We partition our data with like a 5-fold cross validation. We train on selected subset and validate on unobserved subset. That's how we compute the error over 100 trials with random partition. And as you see, the average error is much lower with the LAD approach. Furthermore, it has much smaller variance. Something interesting is even for the listed squares, stochastic gradient descent has a similar variance than the alternating minimization. And here in the experiment, we are using random initialization, but I have to admit that so we don't have any theory for the convergence from the random initialization. We only present the local convergence result, but it's kind of the future direction we'd like to pursue later. We have similar observation on Boston housing price data. Again, the LAD-based approach shows much lower mean error with very small variance. The empirical performance is good, and we'd like to develop some theoretical analysis of the behavior of this robust LAD alternating minimization. That's our main results. And to analyze the performance, we are adopting the typical setting, the standard setting in the literature, given covariance vectors. So we are injecting some contaminate observation with certain probability p-fail that correspond to the portion of outliers. And for inliers, if we don't have any noise, then we have some clean noiseless observation through Max-Affine model with grounded truth parameter. And outliers, the magnitude can be anything. But there is some technical subtlety here. So we will assume that the index of outliers is arbitrarily fixed. We are not considering adversary respect to the choice of the location of outliers depending on the data. But the magnitude can be arbitrary, it can be even adversarial. So that's our setting of analysis. And the question is, how do we show the recovery, the exact recovery of the grounded truth parameters when the portion of outliers is limited by a certain number? And we would like to quantify the threshold, how it is determined to guarantee the exact recovery of the parameters. And our theorem says we fix the model order K and the grounded truth parameter. And we are not, in principle, we can consider like a uniform guarantee that apply to any grounded truth model within certain restriction, but just to simplify the dependence of sample complexity on the model, the dependence on K and like those other geometrical aspect of the model parameters is more complicated. We intentionally hide them by fixing the order and the grounded truth. We also assume that covariance vectors x1 to xn, IAD, and sub-Gaussian, satisfying anti-concentration. And our assumption is there is some threshold on the number of outliers, the portion of outliers. The threshold is determined by only model order. It's independent of the total number of variables. That's important. Then, given those observations, our theorem says if the number of observations exceeds certain threshold that grows in polynomial in K and linearly in D log up to log factor, then with high probability, we were able to show the linear convergence of the error. The error metric is given as the summation of the L-trinom of the error in each affine model. Then it will show the linear convergence. Because we are not injecting any extra noise to the observation, so once we tolerate the outliers, it will provide exact recovery, regardless of what are their magnitudes. But it's also possible to extend the analysis in the case the data is contaminated by both outliers and noise. Then the assumption on covariance for sub-Gaussianity and anti-concentration is standard. It has been already explored in the literature. It applied to beyond Gaussianity. It applied to the uniform distribution and all isotropic low concavity family. So that means the theory applied to a broader class of data. And to observe the linear convergence, we did some experiment and synthesized data. And again, here, the interesting thing is, I mean, as Maxime asked about, because this optimization problem is non-convex, the initialization is extremely important. We did two experiments. We first started from some close point to the ground truth by injecting some random noise up to a certain amount. Then if we started from very close to the ground truth, it showed a very fast convergence, as you see. Even after 3 iteration, the error drops below 10 to the minus 5. But if we start from random initialization, it converges a little bit slower in the first p iteration. Once we get into the basin of contraction, now it shows very fast convergence. I think similar phenomenon has been observed in many papers in the literature. And in particular, the Dominic and I also investigate similar behavior for the rank constraint, the least squares. I mean, this is typical phenomenon for the convergence from the random initialization. Unfortunately, for this particular problem, we haven't come up with any theoretic analysis of the initialization or convergence from random initialization. But we are working on some modification of the previous spectral initialization, but in order to tolerate outliers in the initial estimate of parameters, so we have to incorporate a more geometric approach. So that's still under investigation. Next, I'm presenting the page transition. So here I want to count the empirical success rate out of like 100 repetition. But what we want to say is, in order to invoke the theoretical result, or in order for the iterative algorithm provide exact recovery, the number of observations should exceed certain threshold. And the point of this experiment is how the transition bound scales depending on the number of total variables D. So as we predict in our theorem, it should be proportional to the dimension D up to log factor. That's what you also observed in the empirical case. Here we just designed the outliers by flipping the sign, but even in other models, as we add some noise or making zero or making it like a huge number, actually how we set the magnitude doesn't change the result significantly. That's what you observed. In terms of the robustness, we'd like to determine how much portion of outliers that we can tolerate. Obviously, according to our expectation, if we apply the least squares based method to the robust regression problem, it can only provide some success with lots of observation only when the number of outliers is very small. The reason is we are flipping the sign of our data by I when I belongs to the set of outliers. So that means in terms of the energy of the noise, it's non-trivial distortion. That's the reason why like least squares based method can tolerate very small fraction of the noise. But with our LAD based approach, so you can tolerate the portion of outliers to large number. So here we increase the probability of failure more than 30%. Still, we require more observations as we increase the portion of outliers, but still, so we can get satisfactory success rate as we increase, and that's what you observed. It corroborates our theoretical finding. So now I'm done with the first part on robust regression before I switch gear to the next topic. And is there any question on the first part of result? Okay, then I'll just move on to the second topic. In the first half, I considered the variation of Max-Affine regression when you have outliers in the observation. In the second topic, so I'd like to combine the Max-Affine model together with the variable selection. So that means in the regression model, our output variable y is given through the Max-Affine function plus additive noise. But here we assume that not all D variables contribute to explain alpha variable Y. We assume that only just a few of them active in explaining Y. So that means if we consider the parameter vector for each affine model hyperplane, the parameter is sparse. That's what you assume. So the variable selection for linear regression has been well studied. There are celebrated lasso and basic pursuit and lots of extensive theoretical analysis of those methods in the literature. And we just Googled relevant papers with the keyword variable selection and nonlinear models, and we found a collection of papers. But what we found is their goal was quite different from our objective. And the goal is they want to consider nonlinear model regression problem, and they wanted to approximate nonlinear models through some basic expansion like the spline of certain order. But what they wanted to do that is to optimize the sample complexity. They assumed that the model is simple enough. We don't need a components in the basic expansion up to high order. There's some sparsity in the weights in the linear combination of those components in the basic expansion. They wanted to identify which components are active in representing the nonlinear model. That was their utility of variable selection, but it is very different from finding active variables to explain the output variable. So there's a certain distinction from our work. So we'd like to directly identify which variables contributed to explain alpha variables through this Max-Affine model with unknown parameters. That's our goal. So here is one example. We're considering regression problem that arises in the labor equation model in economics. And they are considering explaining the gross domestic product as some complicated function. Here, capital letters are variables. So G is our target alpha variable, gross GDP. And the L, H, S, D, K, all those capital letters correspond to the specific factors in economics. And they are related through this linear combination of the multivariate function weighted by C1, C2, C3, and alpha, theta, gamma, delta. They are kind of the exponent. But we call it as exponential polynomial because if alpha, theta, gamma, delta, if those quantity exponents are integers, then it's a low-rank polynomial, but it's more than that, so they can take real values. In the sense, we call them the exponential polynomial. That's the typical model in economics. And given examples of this equation, how can we regress the model to find the parameters? That's the goal. And here the trick is, if you apply the log-log transformation on all variables, you take the log on output and take a log on all input variables. So with the weight psi, then the relation between G and the Y and X is given through the softmax function in machine learning. In particular, as we take the limit of this weight psi to decreasing toward the zero, then it reduces it to exactly maximum instead of softmax. Then it reduces it to Max-Affine regression. But what you observe here is that if we see each summand in the model, in the original exponential polynomial, and it doesn't involve all variables in each of the summand. Each summand involves only a small subset of the entire variables. So that's the reason why you observe the sparsity. For example, if you see the first term, L to the alpha, H to the theta, S to the gamma, D to the delta, it only involves the 4 variables. The second term only involves 1 variable K. The third one, it only involves 1, 1, minus 1. So in that sense, so we observe the sparsity. So that's the reason why we want to identify the support of these weights. So now, we are not worrying about outliers. We are going back to the least squares fit. That's more natural. And we'd like to minimize this cost function, but similar to like the variable selection in statistics or compressed sensing and signal processing. So we'd like to inject this sparsity as an explicit constraint. So similar to iterative hard cell sorting for compressed sensing, we consider the variant of project gradient. And here, why we call it the variant is that it's different from the traditional projected gradient. In particular, because of the maximum function in the model, the model is not the cost function is not smooth and not differentiable. There's no gradient, but we can use again the generalized notion of gradient by Clarke. Then we can derive the project gradient, and we just repeat the generalized gradient update on parameters and project it back to set of sparse vectors. It's very easy to calculate by star sorting. In particular, for the gradient step, so we can mimic what we have done in the previous robust Max-Affine regression. So that is, the given parameters, we just define the indices of each sample to see which model maximized at that point. And once we compute those indices, we compute the empirical probability. Then, with that index, we can also compute the gradient in a closed form equation. Then here's the most interesting part is, so we are not going to use constant step size. We are using very specific step size based on this empirical probability where the covariance or input variable belongs to that particular maximizer set. And this is a little bit different from the vanilla gradient descent because pi jt is always less than 1. Like typically, if you apply the vanilla gradient descent, the step size should be very small to avoid any like divergence. But so now we can still use large step size, and we were able to show the theoretical local convergence, and actually it performed very well in practice. So this can be thought of as some variant of some simplification of the Newton's method or preconditioned gradient descent. Again, I mean, for this non-convex optimization, the initialization is extremely important. So we are borrowing the known method by the Gauss for spectral initialization. But as you will see, this initialization is not yet complete. The idea is, if we recall the Max-Affine model, and there is model parameter beta star j, so we can decompose the model parameter into two portions. That's the normal vector for the hyperplane, that's aj star, and the intercept bj star. And the first step of the spectral initialization is, given the data point xi and yi, we construct certain matrix that we'll see in the next page and estimate the span of the hyperparameter hyperplane normal vectors a star 1 to a star k. Then once we know the subspace, we reduce all our data into lower dimension. And in the lower dimension, we do the discrete search. I mean, this is very brute force. I mean, if we know anything about our cost function, and if we don't have any analytic form, and if we cannot anything, then maybe the simplest thing we may attempt is construct a grid and do evaluate the value and find the minimum. Then that'll get you the minimum, and it's a local minimum up to certain resolution. Basically, discrete search is very similar, but we are not using regular grid. We are constructing some net and finding the net, but unfortunately, the second step involves complexity. It scales exponentially in the number of parameters. In this case, fortunately, the dimension is by k, not the d. So that means the model order can be much smaller than the total number of variables. That's nice to see. If we go over more detail for the subspace estimation, we are generating the usual proxy matrix. Typically, the matrix M2 hat is what you see in like other application, like the phase retrieval, the yi, xi transpose. Subtracting identity shouldn't bias our eigenvector, but it's for the sake of the analysis. For M hat 1, it is just a prox you can see in the linear inverse problem like compressed sensing. But what it says is that if you consider outer product of M1 transpose and M2, then not exactly the expectation, but in their population level, then the M hat is very close to its population level matrix M. Then, so actually the M will span the subspace spanned by the grounded truth numeral vectors A star 1 to A star K. Then that can be estimated through principal component analysis. Then, but in our case, unlike the vanilla Max-Affine regression, we want to utilize the sparsity. But now, in order to apply sparse PCA, we are adding extra assumption that all numeral vectors are jointly sparse. In that scenario, then we can use sparse principal component analysis, and that shows significant gain over PCA. That's something I represent later in theory and empirical experiment. Then we can apply the Kolesky decomposition to find the projection matrix. And the remaining discrete search step is really brute force. Once we know the subspace basis, then we construct a unipole and construct covering. Even constructing covering is not easy. The complexity scales as exponentially in dimension k. But furthermore, as you will see, the accuracy of discrete search has closely to do with the resolution R, that's the separation among 2 points in the covering. And that's the reason why the second step is very expensive and not practical. Anyway, if we construct our covering, then we are searching over all combinations of K selection out of covering and just to do brute force search, how it fits to our data. Then once we find the optimal solution within that discretized search area, then we define a search, then we find the optimal solution. That's how we initialize the parameters. So let's see the performance of the SPGD algorithm. Then in theory, by assuming the same condition of sub-Gaussianity and anti-concentration of covariates, and we assume the sub-Gaussianity on independent noise samples, then if the number of observations exceeds some threshold that scales with the accuracy epsilon and noise variance sigma g and s log d over s, then we show the linear convergence. Here, in the noiseless case, the sigma z becomes 0. There is extra dependence on epsilon. So that means we can achieve the linear convergence without, that dependence. We can achieve the exact recovery without with linear convergence. For initialization, so we have to assume the Gaussianity. I think that the necessity of the Gaussianity has to do with computing the expectation. Because of the max function in the model, unlike simpler model like the phase retrieval or value regression, computing the expectation is extremely technical. Actually, the main contribution is not ours. We are taking some of the calculation from prior work, even in the original contribution. They didn't conclude the expectation as a closed form expression. They only showed that it can, if you evaluate a certain integral, that will be our spectral gap and expectation, and it's not pathologically small, then it's bounded by some constant, but there's no clean form. That's kind of limitation. But one of the key trick in their derivation was Stein's lemma, and it only applied to Gaussian random vector. Actually, there has been some extension of Stein's lemma beyond like Gaussian to the symmetric distribution, but that calculation is still very technical. It's also possible to slightly extend the scope of this theory, but I'm not sure whether that's worth our investigation. As a conclusion, if the number of samples exceeds some threshold that depends on the noise level and as a scale log force of p, and we also need to choose the search resolution very small, sufficiently small relative to our desired accuracy. Then finally, we can obtain initialization with epsilon accuracy. That's what we have shown. And the proof of this initialization guarantee is based on the perturbation theory of the sparse PCA. And the only thing we had to calculate is the perturbation of our moment matrix M hat respect to its population level. So that is, we are not taking expectation of M hat, we are taking expectation of M2 and vector M1 separately and construct M matrix from their expectations. But the similarity should be bounded in order to apply the perturbation theory for sparse PCA. And this is what he calculated. And it involves non-trivial concentration inequality, in particular, because of max function and the higher order terms, then it's no longer sub-Gaussian, and we have to use sub-Weber concentration. And we found one interesting small quiz questions during our proof. So that is, we remember the definition of sub-exponential variable, so that has sub-exponential tail. But here, interesting thing is, in the exponent, the denominator is given by sub-exponential norm, but we have the 2 for the symmetry of the tail. And so so in the literature, this result is considered as very straightforward and well-known result. So that means if we are given like k sub-Gaussian random variables, and as we consider their maximum, the sub-Gaussian norm of the maximum will increase by factor log of the 2k. But we try to find it from the original reference, but most of the papers refer to the classical book like the Ledoux and Talagon, but we didn't find the exact statement in the references. So my student Haitham wanted to prove it by hand. So actually, it turns out very elementary but interesting observation. So we can utilize the constant factor multiplied to exponential tail. So that means if we consider the tail probability of the maximum, we can simply use the union bound. Then it will just amplify the exponent to the factor to the exponential function 2 by 2k. But I'm redundantly taking the minimum between 1, because in the end, so we are going to compute the upper bound on the probability. And if the probability becomes bigger than 1, it's meaningless upper bound is trivial. So in order to make it meaningful, we keep using this minimum with 1. That's what it is. And after amplifying the factor to the exponential function by 2k with the union bound, and we can easily move this factor into additive term of this 2k. And here is the trick. And this is the original red curve is original tail probability. But so what you can do is we'd like to upper bound with another probability. So that has very small bias. Just because of the 2 in our desired probability, it plugs as the log of 2 as a constant small intercept. So we were able to upper bound the exponent. This is our original exponent in the red, and this is our new upper bound given as green. But if we see the entire range of the parameter t, it's not a valid upper bound. But here the trick is if the exponent becomes bigger than 0, so we don't care because like e to the 0 is already 1. So that's the trivial upper bounded probability. We only need to upper bound this red curve when the t is larger than certain threshold, that makes the probability 0. So that means we were able to get this upper bound green. So that's how we obtain this new upper bound. Then the denominator will just increase by this increase the slope with the smaller intercept. That's how we obtained this inequality. It's elementary, but it was a fun exercise to us. If we look into the empirical performance of the project gradient descent, SPGD, and we first observed the dependence of the phase transition boundary on the total number of observations D, the total number of variables D. As we expected, it doesn't scale linearly in D, and it only scales through the log function. That's what we observed in Monte Carlo simulation. And regarding the dependence on the number of active variables S, then we had sublinear because we have S log D over S. So actually, if we fit this function with up to some constant, then it matches well with our phase transition. But we had one question. As you see the graph, so when S is really small, then there is a little bit below report. And the reason why we see higher error for small s is if s is relatively small compared to the model order k. So that means we are generating like a k affine models in very small dimensional space. So that means there is non-trivial correlation among the affine models. That makes distinction of models from their combinations through max more difficult because the models look becoming similar and similar. That's the reason why we have worse performance when S is very, very small. Well, that's kind of expected. Regarding the dependence, performance of the initialization, so we'd like to compare how how does injecting sparsity improve the accuracy of the initial estimate? So we compare two methods in two steps. First, we compare the capability of estimating the signal subspace by PCA and sparse PCA. If we use PCA in the previous work, then the error decays as a function of number of observations, like this red curve. And if we use sparse PCA, it decays much faster with much smaller error. But for our own curiosity, so we'd like to fit the decay rate respect to the linear decay and the decay respect to 1/square of n, but actually our theorem predicts something between. Actually, that's what the empirically observed too. So in the sense, our theoretical knowledge seems sharp. And in the second step, we didn't attempt to implement the R covering search because it's very expensive. It's not practical. So what we have done is instead of doing R covering search as exhaustive search, we just selected M random samples and tried them to see, just apply a few iterations to see which sample is good. And so what it is, as we increase the number of trials with the random search on the net or just random sampling from the subspace, the error decreases. But if we compare the performance with PCA and with sparse PCA, then sparse PCA start from more accurate estimation of the subspace that ends up with faster convergence of error toward the zero, so with a pure attempt. So that's what we observed. Finally, as a summary, we considered two variations of the Max-Affine regression. So we presented robust convex piecewise linear regression by alternating minimization, and we showed the local convergence guarantee, but the initialization part is still open, so we are working on it. And for variable selection, so we showed the local convergence of project gradient descent and performance guarantee of spectral initialization with sparse PCA, but still, we are not fully satisfied with the performance because discrete search step is not practical. So we are investigating other initializations that doesn't involve discrete search or convergence from random initialization. And so our second part has been posted to archive a few days ago, and first part we are still working on it, will be available soon. And as a final remark, why are we still interested in Max-Affine model? These days, people are looking into fancy models like deep learning or transfer learning. So can Max-Affine compete with deep learning or transformers? So our thought is still there are many scientific questions. So when we'd like to understand the relation between key factors in the experimental study or some theoretical modeling, how they interacted together. But not in every application, the number of variables scales like a zillion, like in text mining or the multimedia data, like computer vision, like the large language model. I mean, if we work with really huge models, maybe transformers or deep learning, they might provide more efficient parameterization by reusing the repeated structure or sometimes with convolutional structure, but they can be more beneficial. But in small size or moderately sized applications, where it is more important to have better intuition on how to train our models with a more easier to interpret, procedure, then I guess still the Max-Affine model can be beneficial. In particular, as we consider the extension of the theory to the difference of Max-Affine case, then we don't need to restrict our model to the convexity case. Then I guess still there can be an interesting venue to further investigate. I think that's it for today. Thank you so much for your attention.